Let's start. Let me start by showing you a map with 3 million points. It's terrible. You cannot get any meaningful information out of this one, right? But if I show the same data a different way like this, then you have a better idea what's going on. You know that there's some things happening more frequently in the southeast part of the United States compared to any other part. So the technique that we use to spatially group point into equally shaped polygons to understand our data better is called feature binning. Good afternoon. Welcome to Dev Summit technical session on visualization and exploration of large dataset using feature binning. My name is Tonu Hawk. I'm a product engineer working in the core ArcGIS Pro team. Joining me here today is Said Parirok. He is a developer from GeoDatabase team. In this session, we'll be talking about feature binning, a new capability that was introduced in ArcGIS Pro 2.4 and ArcGIS Enterprise 10.7.1. Even though we made the user experience a lot better, easier, and integrate this with rest of ArcGIS platform, the concept of binning is nothing new. It has been around in ESRI product since the workstation Arc-Info days. So what is the purpose of feature binning? In short, it is a technique that allows you to explore your data, such as finding pattern, concentration, trends, etc. over both space and time. And we do that by aggregating data into equal shaped polygon, also known as bins. So now, with that, you have more power to see which other cannot. If I were to put another way, feature binning is all about aggregating and summarizing data. And as you know, aggregation and summarization is not unique to spatial data, right? We do that for non-spatial data as well. Let's take a look at it. So I'm looking at about 144 records, tornado that ever recorded since 1950 out of about 30,000 or 40,000 records that we have. But it's already looked overwhelming. Plotting them in chart does not make much difference. Adding the spatial components actually make it even worse. If I were a cartographer, I could have made this map look better, but it will still not be able to give you any meaningful information. And as you know, map is all about telling a story, and I don't seem to get any out of this one. So the problem with large data set is it's overwhelming. It does not provide any meaningful information. You cannot recognize any pattern or trend. And with a really large data set, it will be slow to draw. So to what we do, right? Instead of looking at the raw data, we actually aggregate and see that summarization of your data. So in this case, I want to see how many tornado we ever had for each category. I can represent them in chart. We can get different answer as well, like in addition to number of tornado for each categories, we can see number of damages or total damages caused by each category of tornadoes. When you actually do that for the spatial data, there are two ways to do that. First is when you have a related records, such as this one where I have a rainfall data collected over the time for each stations. And I would like to know what is the total rainfall for the 7-day total rainfall for a given station. I want to map it. So what I do, I will aggregate them for this window for this 7 or 8 days. Aggregate, I see that result is 1.37 inches. I will join that to that station and draw the map with that information. I can move to the next window. I can do the same thing. And this time it is 2.97 inches of rainfall for that period of time for the same weather station. When the data is spatial, such as this one, which is drawing tornado locations in the United States since 1950, what we do, we aggregate them into known geographical or political boundaries such as states, counties, districts, provinces, etc., which is very useful for decision-making process. but you need to make sure that you normalize your data. Otherwise, if you were to compare one of the counties that are largest county in the United States with some of the smaller one from the New England, it is not a fair game, right? Most likely you will normalize them by area. We can also aggregate them by equal-sized polygons, also known as beans. It helps level the playing ground. Now you can compare beans without any biasness or of artificial boundaries. So at high level, how does feature binning works? So let's say these are the points. What we do, we actually overlay hexagons or our beans on top of points, compute how many points are within each polygon, and assign that value to the polygon, right? So with that, let's go and do some demo. Before I do that, I have a question for you. Is feature binning only applicable or useful for large data set? To answer the question, let me actually go and open a map and show you something. So looking at these two hexagons, you can right away you can think that the hexagon at the bottom has more points, right? But if I actually fill those hexagons with color, you will see though one of the top gets highlighted. The reason it is because it has 104 points compared to the bottom one that has 21 points. So there must be some kind of concentration of points somewhere. I can use my bean size to make it smaller and try to narrow it down to a place where all of them are concentrated. Now if I zoom into that area, you'll see that here there are those all 99 points zoomed into the so small area that when I zoomed out to larger area, smaller scale, they all appear as a one single point. So to answer my question, the answer is no. You don't have to have a large data set. The feature binning can be useful for any small or large data set. Let's do some demo with the real data. So now I'm connected to an enterprise database and I can see I have this point data set, as you see here. And I know that this feature class is enabled with feature binning. The way I know is by opening the property page. And if I scroll down, I can see here it says feature binning is enabled and feature caching is false. So let me add that to my map. So the moment I add it, the first thing you note is that the layer is not drawing with a point. Instead, the points are grouped into hexagons and hexagons are being drawn on the map. If I look at the table of contents, you see that it had two sets of legends, one for feature and one color ramp for beans. On the ribbon, in addition to feature layered ribbon tab, you'll see a binning ribbon tab. Binning ribbon tab has a bunch of commands that helps you to work with feature binning. The very first one allows you to toggle between bean and individual points. It is pretty fast to draw in this case, but it does not give you any meaningful information. But if I toggle back to beans, then I can see clearly where is that tornado valley of the United States. So if I zoom in, you can see that it actually switches from one bean size to another bean size, right? The way it works is that we make sure the beans will never be smaller than a certain size in pixel on the map, right? And if I keep zooming in very further, actually I can think of, okay, this may be a good place where I can see individual points without them being overlapped. So I can actually use the binning switch to toggle, or I can actually set a threshold scale. Now I can see my points, and as I zoom out and go beyond that threshold scale, I see this automatically switches to bean. I can use my bean size control to see my data in greater detail or lesser detail. I can use this bean lock size command to lock the bean size, so when I zoom out or zoom in, it will not change my bean size. I can toggle it back anytime I want to. Okay. The next one is pretty important. Oops, it switches back. There you go. It says that the coordinate system, right? So I can have my beans generated in a different coordinate system than the layer itself. So if I open my layer property page, I can see that the layer is in WGS 84, but my beans are generated or defined in equilibrium projection, which we most of the time recommend, and web Mercator projection. So if I change my maps projection to web Mercator, that's it. Now you see that the beans which is closer to equator actually looks smaller than the beans that are actually further away from equator. Even though on the map they don't look the same, but in real life they actually represent exactly the same area. So it actually it's fair to compare this bean with the one at the far right corner. Okay, but for some reason, for cartographic reason, maybe you need to have your beans showing the same size on the map. In this case, you can switch to web Mercator, and this time they will look the same, but in the real life, in the real world, they will not represent the same area. Okay, which again we do not recommend, but if you have to do that, you need to find a way to normalize your data to make this map meaningful. Let me undo my changes. Okay, next button in that in the ribbon is Symbology. So if I open my Symbology pane, you will see that a layer that is enabled with feature binning actually allows you to set symbology for bean as well as features independent of each other. If I go to the features, right, I can import a symbology and assign an unique value renderer from an existing layer file. So now that it is assigned, if I zoom in further enough, I'll see those individual points appearing with the unique value renderers. Let me zoom back out to United States. The Symbology pane, of course, have this bean tab that allows you to define different symbology for the beans. Right now, we only support single symbol and class renderer. For on-class renderer, you can, of course, change the color ramp to anything that you like. Okay. You can see that these are the areas that highlighted in the dark blue, which basically represents about 3064 or more points in that area, in those beans. But in some cases, you really want to know exactly how many points we have for each beans. In that case, you can click on the template symbol and go to Properties. And the Properties, click on that symbol tab, and then there is a symbol layer we have. You can uncheck it. You can change the font size, apply, and now you can see those numbers. So this polygon, these hexagons right now has 3591. As I zoom in, you'll see that it switches to different LOD or level of details. Now this polygon, this one, which is smaller in size and has 809 points. Okay. So you see that as I zooming in and zooming out, it's my TOC right now. My TOC says it's the maximum value is 911. If I zoom out to that, this LOD, it says the maximum value is 3064. So how does it compute this upper value for my my color ramp dynamically? To do that, what it does actually, when you apply that, when we enable feature binning, it actually computes some rendering statistics. That basically means that it computes an average value for that level and also computes a standard deviation, right? What is the spatial distribution of my value in all my beans? And then by default, it uses two standard deviation to apply color ramp or to compute that upper and lower value. Or it provides you other options. Like in this case, I can choose 1/4 of the standard deviation to display my map, and I can see it's drawing this differently. And you see that the TOC is updated already. So you would like to know what are those maximum and the minimum value or upper or lower values that's used in that color ramp or the histogram. You can actually switch to custom mode and you can look at it. So here it is. I'm looking at my current level of detail. The way I know it is by looking at that gray bar, right? That information is also available if you hover over on the bin size control. You'll see that information, like which level you are currently at. There are some cases, let's say I'm actually switching to use maximum magnitude value in my area. So basically I want to show my bins with that maximum tornado that ever hit in that area, right? And I know that the maximum value cannot be more than 5, but in the table of contents, the value that's automatically read, it says 6. I want to change that. I can change that just by typing that value into those cells. And now you can see those are been applied everywhere, and you can apply that to all the levels if you want to, which is great, right? Now, how about editing? How does editing work, right? So feature binning, again, the underlying data is point, so you will be working as if you are actually editing a point data set. Let me show an example. Before to do that, let me zoom into an area very close to Aspen, Colorado. Make the bin size a little smaller. And then let's say there are some burst of tornadoes in that area. So let's start with a tornado of category 2. The moment I added that point, you see that the hexagon appears with value 2. That means the maximum tornado that occurred is it's a category 2 tornado. Let's say there was another tornado hit an area that is a category 4. Now the cell is updated with 4. Let me switch back to my symbology, and I want to show my bins with shape and features count, right? How many features are in that cell? You see that there were only 2 because I only added 2. Let me add some category 1 tornado. As you see that the moment I'm clicking, it's updating that. Cell is getting updated. It's getting darker and darker, and the value on top is getting updated. So there are 24 points I just added in that area. So if I switch back to my to see my point data set, you'll see all those 24. I can use my select tool exactly the way I could have done it for any regular layer, and you see that at the bottom of that map there are 24 features selected. I can switch back to display bins, right? There the features are still selected. I can use my delete tool to delete them. As the features are deleted, the hexagon is removed as well. So you see that editing is dynamic and it happens real time. So now that we know all the capabilities of binning, how can we enable one? Enabling is pretty easy. So all you have to do is to run a geoprocessing tool. You can search by bin keyword, and those tools are available inside data management tool, feature binning tool set, and here is the enable feature binning. Yeah, and there is a tool, run the tool to enable a feature binning. I'll get to that in a second. With that, let's get back to my slides. So to recap what we just learned so far is that feature binning is all about exploring your data over space and time. We added that in ArcGIS Pro 2.4. It's all about aggregating point features into multiple level of bins at multiple size. Each level defines different sizes of bins. We have that option to define the scale so that you can automatically switch to point features or bin mode. Feature layers that's enabled with feature binning has 2 sets of symbology so that you can work with or define symbology for bins and the features independent of each other. If you want to show the value on top of bins, you have to click on that template icon and then make sure that symbol level is checked. Editing is real time and very dynamic, as you saw that in my demo. Okay, to manage feature binning, ArcGIS Pro ships with 3 new geoprocessing tools: enable, disable, and manage caching. So in that enable feature binning screenshot, you can take a look at that. I have as an input feature binning. I choose a bin type. You can have up to 2 bin coordinate system. As I told you, they don't have to be the same as the input feature. And then optionally, you can add summary statistics. By default, the shape count or feature count is there always. But in addition, in this case, I want to see what is the maximum tornado that ever hit in that area and the total damage caused by all tornadoes. If my data were really, really large, I could have enabled feature binning cache so that I can take that cost upfront, but while displaying it on the map, it will be much faster. If my data gets updated when the binning cache is enabled, I need to use Manage Feature Binning Cache tool to update my data. So now that we learn all those capabilities or the commands that's available with feature binning data set or options, how can we use it to explore my data? As I keep saying it, feature binning is all about exploring it data. So we can, in the next demo, I'll be showing you how to use the different filters and summary statistics to help us find some pattern and explore my data. Okay. With that, I'll switch back to this map, which is exactly the same map that I showed at the very beginning of my session. Right? Again, this map does not make any sense, but if I switch to displayed in the beans, I can see that it's a clear pattern, but it is showing the data that I have here is actually all the US fire occurrences between 1992 and 2015 for 23 years of data. So living in California for over a decade and reading all the news that I found, I had this perception that fire only happens in the western side of the United States. When a lot of beans are actually lit up in the southeast corner, that actually made me think what's going on in that area. So let me zoom into southeast corner of Georgia. I can see when I zoom in, I can still see that they're pretty highlighted. There are very concentration of fires in that area. Okay, so I want to zoom in further, but I just don't want to change to a different bean size. So I'm locking my bean size now. Now let me zoom into Helena, Georgia area. Okay, now I see that right there. Those are highly concentrated area. Now if I switch to see individual points, I see that lots of blue stars. That basically means those are debris burning. If I zoom to Dayton Beach, Florida area, I see the similar pattern almost in that western side, but the rest of the area is filled with symbols that represents lightning. So most of the fire that happens in that area caused by lightning. Let me switch back to binning and unlock my bin size and zoom back to USA. Now, the data, as I mentioned, it actually uses all kind of fires, but I'm only interested in the significant fires. So with that, what I did, I already have a layer that shows that. So the way I did that, if I open the property page and go to the definition query, you see that I'm only using point data set points that actually has this ICS 209 incident number, which basically means those are significant fire, not debris burnings or something like that. So now the map that I'm looking at matches my perception that most of the fire happens in the west, but I also find that interestingly, which I was not aware of before, there are lots of fires in Florida and Appalachian Mountain area, and to my surprise, I did not know about that one, in Oklahoma. When I digged around or asked around with my folks, they told me that it happens because of the brush fires. Right? That's just cool. I learned something today. But as an analyst, you may not always need to see a map that shows only the number of fires that ever happen in that one. You also know the area that's the total area burned by the fire during that period. So you can see that again, most of the areas that burn in the western coast, right, again matches my expectation. And now, but there are cases, it's just not the total area. You want to also know the average burned area. So I have this map and I would like to display that with average area. So I click on my symbology to go to the symbology pane. In the bean tab, as you saw, it's already displaying with a single symbol. I'm switching to unclassed renderer, but in my summary field list, I don't see any summary statistics that I can use to show average fire size. So what happened is that when that feature class was enabled with feature binning, it was enabled with only 2 summary statistics. So what are the options that we have now? Now I can actually disable feature binning on that feature class and re-enable that with average file size, which might not work for me in this particular case, or you may not be the owner or right access to that feature class to enable that. In that case, what you can do, you can actually use the summary statistics page that accessible from summary statistics command on the ribbon and add a new summary statistics. In this case, I'm adding an average file size. Once I added that, it shows up in this drop down box. I choose it, and now what happens is that the moment I choose that, since the statistics is actually defined at the layer level, it needs to compute some rendering statistics. Remember the time I mentioned before, rendering statistics is all about finding what is the mean or average value for each LOD or level of details, and what is the standard deviation. Now let me change my color scheme to match with my other layer. Okay. Now I have this map that shows the average burned area by all the fires between 1992 and 2015. Now if I show them side by side, you can compare how those 3 maps look like, right? Now you can see that this is on the far right. This is showing on the number of significant fires that happened in those 23 years. This is the area that's total area burned by all the fires, and this is the one that shows the average area burned. So we have actually three different pictures from the same data set. Now if I actually go to Alaska, which I did accidentally while I was working with that one, and I had no idea that could be any fire in Alaska. With my surprise, I found there are some significant fires in Alaska, even though the number of fires is not that much compared to the rest of the United States. But look at the total area that burned, and the average area that burned by those fires are really, really high than any other part of the United States. Now I'm interested to find out what caused all the fires in Alaska. So if I zoom in and switch to see individual points, I can see those are caused by lightning, right? Now, while I'm looking at the TOC, there are 2 things that caught my attention: is power line and railroad. So there are some fires that actually started by power line failure or something, or spark and railroad sparks. Okay, now I'm interested to find out which area where do we have more fires generated by power line failure or railroad sparks. Now, so to do that, let me go back to my original layer. And this time, this layer, actually, I authored them with some definition query. So let me switch to showing the power line. I want to see all the areas that are can I see any pattern with the fires that ignited by power line failure. Now, one thing you see that it's get washed out. So reason it gets washed out is because this color RAM, when it was defined or created, it actually used all the data set, the 23 years worth of data, right? But now that I have a data definition query set to that layer, these values are too much for that one. So I need to recompute or update my statistics. So if I go back to my Symbology pane under Bin tab, there is a more menu. I can have this use this refresh value option to update my map or update my layers render statistics. So that now I can see it's a better map, right? I can see that, make it smaller. I can see that most of them are actually in the Texas area. How about the fire that actually caused by railroad? I see that now the pattern shifts to Florida area. I was wondering whether that could be because of there are too many railroads. So if I drape my railroad layer, I see that, yeah, there are lots of railroad, but compared to Midwest, there are not that too many. So there must be some other reason it's happening. So if I make that smaller, you can see that most of the fires, as we expect, it follows the railroad, but some reason something's really going wrong here in the Florida that causes them to cause a lot of fire in that area, and we need to find out what's going on. Okay, so that's great. So I can see all different patterns, concentration, and everything over space. How about seasonal variation or things that changes over the time? So this time what I will do is I want to see what is the seasonal variation with my fire data. To do that, I enable range on my layer. I use my fire month attributes, and 1 being January and 12 being December. So now if I use my range slider from January, then as I approaching summer, you'll see that there are more fires happening. This is the peak time, July and August, and you see the lots of red area. And as we're approaching the fall and winter, there are less number of fires. So this is using all the data for 23 years. I was curious to find out whether the same pattern can exist for a single layer, single year. So I'm sorry. For that, I actually make my layer time aware. Now then, made my time slider enable, and I go to year 2001, 2006 for 1 year worth of data. Now if I go to and go from 1 month to another month, you see my data is kind of washed out, right? Again, it's because when this color ramp rendering statistics or the upper value was computed, that was using only the range filter. But now that I have time filter enabled, that is no longer valid. So I need to update my layers rendering statistics. To do that, again, go back to my Bean tab on Symbology pane, and now I have another option called refresh value using ranges. So when I use that command, it actually updates the rendering statistics with both time filter and range filter. Now I see that, of course, in month of July there are lots of fires, August the same thing, and as I moving to fall and November, December, I see there are not too many fires in the United States. So you can see that the feature binning gives a lot of capabilities, right? You can use different filters like a definition query, temporal filter like the time slider, or range filter to slice and dice your data to find different patterns or concentration or trends, right, from your data that you're not able to see without this technique. Summary statistics, as you saw that one, you can define summary statistics both at the database level, where you can have up to 5, or with the layer. In the screenshot, as you see, the summary statistics that are shown in gray, those are the ones that are defined at the database level, okay, and the ones that are not in gray, they are defined at the layer level, okay. And you can use the summary statistics to symbolize beans or even in pop-ups. When feature binning is dynamic, there is no performance difference between whether they are defined at the database level or layer level. They work exactly the same way. But so what is the advantage of defining at the database level? The advantage is that the rendering statistics gets pre-computed. So when you switch between summary statistics, it will not bring up this computing rendering statistics dialogues. That will be much faster. And anyone who can access that feature class can use them right away. They don't have to define anything at the layer level. Also, when you add that summary statistics to the layer, okay, so let's say you want to add a new summary statistics. If this feature binning is dynamic, in that case, first you have to disable and then re-enable feature binning with the new summary statistics. But if your feature binning or the feature class is already has this binning cache, then you have to run that manage feature binning tool again to update the feature class with new summary statistics. So you see the lots of different capabilities with the feature binnings. That's a very exciting, right? But there are some things you still cannot do, such as like you can add that feature binning in a 3D map, but you cannot extrude those beans in a 3D fashion. That's the limitations that we have right now. Or we have some basic statistics support, but what if instead of showing the maximum, showing beans with the maximum tornado that ever hit, I just want to know what is the most frequently hit tornado, category tornado in that area, in that each bean, right? That's called predominant value. You can extend that to crime data, for example. You want to find out what is the predominant crime in that area. So those are things that we don't support, we do not support out of the box, but we have some advanced SQL expressions that you can use to achieve those advanced analysis. So Syed will take you to that one. See, he will also talk about how actually binning works down below the database level in the very detail and give you some exciting advanced analysis. With that, I'll hand it to you, Syed. Take it away. Great. Thanks a lot, Syed. So you see that the amazing capability that you can achieve, or advanced analysis that you can achieve by using SQL. So there are the next few slides. We just simply show those SQL statements that Syed used in his demo, just for your future reference. So let's talk a little bit about feature binning cache. As I said, when your data is really large and generating cache dynamically takes a really long time on your map, it's better to take that cost upfront and actually define caches at the have those beans cached at the database level. As I told you, the way you can do that is by checking that generate bean cache in the enable feature binning geoprocessing tool. So when you actually do that very first time, it does not actually create caches for all the levels. It actually finds some optimum cache LOD size, and then it actually generates only up to that level, right? So, and then if data gets changed, of course, you have to run the manage feature binning cache geoprocessing tool to update your data. So when to update? When data gets updated spatially, you want to add a new statistics, or you want to alter the level of caching. Like say when you run that enable GP tool with that caching option, it generates caching up to level 10. But you think that it's not good enough for you, you want to cap the cache generated up to level 14, you can do that. So there are some scenarios when even though you have feature class enabled with feature binning cache, the cache gets ignored. When you actually have some summary statistics that's defined at the layer level, or you use one of the following filters, right? You define definition query, you specify time or range, then the cache gets ignored and it makes dynamic queries to the database, dynamically generates that aggregation value. How to choose cache level? It all depends on the data. Like if your data is global data, you may get away by generating cache up to level 10, 12, but your data is for a small area such as like Manhattan in New York City, then you may want to go it up to, I don't know, level 18 or 12, 20 or something like that. So it all depends on your data. So as I said, the cache are not generated to all the way to the last level because it actually takes up a lot of storage. And so what happens when you actually zoom beyond that? Does it stop? No, it doesn't. At that point, actually, it dynamically generates those beans or aggregate the results dynamically. And we found that when you actually zoomed in a very small area, creating those dynamically generated beans was very fast. Okay, so To review what we learned so far, again, feature binning is all about help you understand your data, explore your data, find out some patterns, try to understand and comprehend your data over space and time, because those are very critical components that we have with the GIS data set. It helps you ask the right question. You saw me in my second demo. I was seeing some concentration and I was interested, I was intrigued what's going on in that. Helps me find out some interesting patterns. Right now it's only available on enterprise databases. Currently it's not supported on file database. It only supports for point features. Line and polygons are not supported. And we just talked about feature binning cache just moments ago. Once you have that layer, if you want to share that with other people or within your internet or across internet, you can share that out as a map service or map image web layer, and then you can consume that back in ArcGIS Online Map Viewer or in your handheld device using ArcGIS Collector or other application.
In part one of this presentation, Tanu showed you feature binning out of the box and its capabilities in ArcGIS Pro. In part two, we're going to take this step further and we're going to extend the feature binning capability using SQL in your relational DBMS. Here in ArcGIS Pro, we have a point data set which represents crimes in LA between the years 2013 and 2015. There's about 500,000 points here. When we look at this data set, we don't glean a lot of information. It's just a dense blob of points. So the first thing to do, of course, is to enable feature binning on this. I've done that here, and we can begin to see a little bit more information about these points. We can see what areas are dense, and we can also look at certain statistics that come out of the box. You know, whether that's a sum, an average, min, mean, or standard deviation of whatever attribute we're interested in. Sometimes there are questions we can't answer with those summary statistics. For example, of these crimes, which ones are the most predominant value in each individual cell? Those are questions that we have to answer when we extend feature binning using SQL. We actually have to go to our relational DBMS, generate some custom SQL so we can answer these more complex questions. Before we can write custom SQL, we first have to understand a little bit about feature binning, the implementation, the information model, so that we can take advantage of those things when we're writing our custom SQL. So underneath the hood, all feature binning really is a discrete global gridding system, also known as a DGGS. This is really a mosaic which covers the entire Earth's surface. The rigorous definition is a set of non-empty regions that form a partition of the Earth's surface. For our purposes, we can just think of it as a grid which is overlaid on top of the Earth. There are different types of discrete global gridding system. There are DGGS, which are at a single level. There are also hierarchical discrete global gridding systems. Feature binning uses the hierarchical flavor. It really just means that for each one of these cells or partitions, we divide it up into further partitions, and we do this recursively until some set resolution. For feature binning, we stop when cells are roughly about 1 meter squared. There are some famous discrete global gridding systems out there. There is the GeoHash, which is a public domain geocoding system, and it encodes a location into a short string of letters and digits. It is hierarchical in nature, and what's nice about it is the letters and digits are short because it uses a 32 base encoding scheme. I'll explain a little bit more in the next slide. Google's S2 geometry library is also another famous one. It's hierarchical as well, and they use their gridding system as an index to provide fast search access. It's also something new called What3Words, which is non-hierarchical in nature, and they use 3 words to uniquely identify each cell. Their resolution is roughly 3 meters. So what are the DGGSs supported by feature binning? We support GeoHash, which partitions the Earth by longitude then latitude recursively. We also have some homegrown Esri systems, GeoSquare and GeoHex. GeoSquare partitions the Earth into squares, and GeoHex actually uses triangles, and the reason is that hexagons don't decompose perfectly into other hexagons, but triangles do. So we're able to use the triangles and come back after the fact to recompose the hexagons. If you're interested in GeoHex, go ahead and post up on GeoNet or send us an email. We can give you more information. To keep this demo simple, we're sticking with GeoSquare for the remainder of it. Okay, so for our GeoSquare implementation, how do we uniquely identify these cell names throughout the entire grid system? Well, here we're at the top of the world, and we partition it initially into 4 cells, A, B, C, and D. And you can think of these cells as hemispheres of the Earth for the moment. Well, as we begin to partition each one of these cells, we simply add a character to the end of it to give it a new unique name. And we keep the relative space the same. So A is in the upper left-hand corner, B the upper right, C the lower right, and D the lower left. And we can do this iteratively for each cell. So you can see B has BA, BB, BC, BD. The same goes for C and also for D. So let's say we wanted to know where this particular cell in the world was, ACCB. Well, there's a couple of facts here about it. It is 4 characters long, so it's in the 4th level of our grading system. And we also know the previous cells that it lives in. It lives in cell A and also lives in cell AC. So if we go one step further in our grid, we can see it's going to be about here. And ACC would live right here, right? ACA would be here, ACB here, and ACC is here. And if we go even another level deeper, we could see that ACCB is here in the upper right-hand corner of ACC. So you see these characters, they build on each other. And as we dive deeper into each level, we add one more character to the end of the string, and so that we are uniquely identifying every cell in our entire system. So how does our information model work? Well, at the time that feature binning is enabled, we'll add new columns to the base table, and these will have a particular structure to them. We're going to name them in a certain way. We're going to call them our special system maintained prefix, followed by the bin type that it is, either square or hash or hex, followed by the SRID that we're supporting. So each one of these encodings are generated in a particular spatial reference. Tony should have mentioned a little bit about that, but different spatial references will actually generate different encodings. That's the thing to remember here. And you can see for each feature that we have encoded it up to a certain LOD. Whenever we stop at 1 meter squared resolution, we'll get that many characters. And we populate it for each feature. So each feature lives in this particular cell, as well as the substring of the cells as we trim them off the back all the way down the line. Okay, so now we're going to stop and go to our SQL Management Studio to play with the SQL a little bit. Okay, so here we are in our Management Studio. Our underlying DBMS is actually a PostgreSQL, and this is our crimes data set, and you can see here that we have 2 new columns, GeoSquare string 2229, which is a California specific spatial reference, and GeoSquare string 10204, which is a equal area contiguous USA spatial reference. So there are those. Now let's look at our base table. And there's only a couple of columns that we're really interested in. the category, this is the attribute which we're going to be taking a closer look at of these individual crimes, as well as the GeoSquare string. And for this demo, we're just going to work with the 2229 spatial reference, the California spatial reference, and we're going to view our map in that one as well. And you can see that all of these individual features have their own encoded bin string as well. Okay, so let's talk a little bit about how to take advantage of this information model. So the thing to look at here is the encoded bin string, and I'll just bring it back up so we can take a look at the same time as we're writing this query. The feature binning query is really powered by this group by, and what we're most interested in is aggregating these points into cells of a certain size. In this case, that size is LOD 17, and LOD is level of detail 17. And so we're grouping by the first 17 characters of the encoded bin string so that we can aggregate all points which share that same bin. So that's that piece of it. And in the select list, we have the unique identifier, the cell ID, which really is just that substring for the first 17 characters to represent level 17, and whatever statistics we're interested in. In this case, we're just going to count the number of features in that cell. Grabbing our data from our base table LA crimes, and we're making sure we filter out any not valid features. So if we execute this query, we should see here are each one of our cells, our unique identifiers, and the aggregations of the number of features in there. Okay, how do we take this a little further and look at the predominant value? Well, in PostgreSQL, they offer us this nice syntax to tell us exactly which attribute is the most predominant within the group. And it uses this mode syntax within group and order by on the attribute that you care about. The rest of this query is exactly the same as previous. We're just adding this additional statistic in grouping by our same LOD. So we'll let this run. We can see, okay, for this cell, Grand Theft Auto is the most predominant crime. Well, there's only one there, so that's probably the only one. But in this cell, something more interesting is happening. Right? There's 150 crimes in this particular cell, and we can see that larceny theft is the most predominant crime amongst the group. Okay, so how do we add a spatial component to this query? Well, in our stgeometry type, we've provided a set of spatial operators. They are not documented, but will include some basic documentation for these. In this particular one, stgeom from GeoSquare will take in a cell ID, a level of detail, and a spatial reference, and instantiate a geometry from that for us. And so what we're doing is we're bolting on this spatial component to the query which we just put together earlier. And if we run this real quick, we can see that we'll get our statistics, predominant category and count, as well as our unique identifier, our cell ID at LOD 17. And we're also getting a shape column here. So now we can take this and we can plug it into Pro as a query layer and visualize something meaningful on the map. So I'm just going to go ahead and copy this query, switch over to Pro, and add this as a query layer. Let's pick my connection, paste our query in, and our validation won't succeed if we have these comments in there. So I'll just go ahead and delete that comment, and I'll name this something. Let's go ahead and validate the SQL. Everything looks good there. Click Next. And we should pick a unique identifier, where our cell ID is the unique identifier. So I'll use that one. And we can see that query layers discovered certain properties about our SQL. The entity type is polygon. The spatial reference, we got our state plane California. and its SRID. So I've already added this and symbolized it. So I'm just going to go ahead and turn that on. And there are a number of categories, far more than these 5, but I just concluded the 5 predominant categories with the largest number of crimes in those cells, and symbolized in this way. You can see that we have large swaths, larceny, theft, which are occurring here. And then following that visually, it looks like narcotics and burglaries mixed in there, and then all these other values are in the gray. So if we want to ask ourselves some more interesting questions, we can begin taking a deeper look at some of these larceny theft cells to see exactly what is going on there. So one thing we could do is we can use some sort of GP model to ask more intense questions. For example, what if we wanted to forecast where future crimes might be of a certain category of larceny theft, for example? Well, we can create this complex GP model, chain all these GP tools together, and maybe come up with something meaningful at the end. Or we can create some custom SQL that'll be real time and will update when we pass it on to managers. So let's take a closer look here. And what we can do is we know that all features which live inside of each one of these individual cells are relatively close to each other, and they share the same cell ID at some LOD. So we can use that fact to do something a little bit more tricky and involved using our custom SQL. So let's flip back to our management studio. We see here that I've created another SQL query which is going to generally do some forecasting for us. And the idea behind this is that the past incidences of crime are going to be a future representation, and we can use it to forecast. So it's our same basic concept. We're doing a group by on a substring of our encoder bin string. Now, why did I choose LOD18? Well, LOD18 is roughly 500 meters squared. So that means that any two features which share this particular encoded bin string at 18 are going to be relatively close to each other, about 500 meters squared, no further than that. And so if we take a look at our select list, we see we have our GDB cell ID, and then some of the statistics we care about. Incident count, I wanted to get the first representation of a crime which occurred in that cell and the last crime which occurred in that cell. And I also wanted to get the difference in days between the first and last crime in that particular cell. This way we can see, is crime recurring there already? If it is, perhaps it's an indicator of future crime occurring there. And in our filters, we only pull out the features which are valid, and we are only looking at larceny theft crimes in this incident. So I'll go ahead and execute this query. And we see we have our cell ID, the incident count, the min and max date of crime first occurring, and the difference in days between those two. Okay, so let's take this back to Pro and see what that looks like on a map. Oh, actually, before that, we have to add the spatial component to it, because right now this is just a table query. So similar to what we did previously, we are just going to bolt on this geometry using our same spatial operator stgeom from GeoSquare, which takes in the cell ID, the LOD, and the SRID. And in this case, this is a typo. That should be LOD18 because that's the level of detail which we care about, and we're grouping by here. Okay. So similar to the predominant category query layer, we're just going to add this one through the add data menu query layer. I've already done that here, so we're going to take a look at this guy. And what I've done with this query is I've symbolized it using the bivariate colors. This way we can get a correlation between the incident count and the difference of days. And here you can see that high correlation is in this purple color. So now we have particular cells which we can target that'll tell us that will be more likely for crimes to occur in the future as opposed to some of these other ones where the correlation isn't as high and crimes might not occur. So you see we've been able to take advantage of the feature binning information model to create some custom SQL queries and provide real-time results to managers who need to make decisions. That's all I got for you. Please send questions and comments on GeoNet and email to us. Thanks.
So with that, thank you very much. We appreciate your time to listen to and watch our technical session. Before Said and I sign out, here are some links to some of the help topics that will help you to learn the feature binning and more. With that, enjoy the rest of the day. Thank you. Bye.